Welcome to the KEI's Networks series exploring decarbonization, GHG emissions to arrest climate change. The focus in the second episode, is about the role of technologies, current and emerging, to address climate change. Today, we expect to learn more about mankind's capacity through technology to contain and maybe even reverse the ever-increasing GHG emissions warming the planet. Our moderator for the webinar is Eddy Isaacs. Over to you, Eddy.
The next presentation is on insights into nuclear fission and fusion. And our speaker is Dr. Axel Meisen. He's the president of the Fusion Energy Council of Canada. He's the former inaugural chair in foresight at the Alberta Research Council. Axel is also a former president of Memorial University of Newfoundland and president of the Canadian Commission for UNESCO. He's also the former dean of applied science and professor of chemical engineering at the University of British Columbia. He was appointed to the Order of Canada in 2008. Welcome, Axel.
Thank you very much, Eddy, and also thank you, Perry, for your thoughtful introductions. Much appreciated, and thank you for mounting this set of 3 webinars. I will now take you into a specialized area, the world of nuclear fission and nuclear fusion. Both nuclear fission and fusion can be expected to make important new contributions to decarbonization, but only in the longer term. However, my objective is not to convince you what these 2 energy forms can do or cannot do. My objective here today is to provide you with some fundamentals and some insights so that you can judge for yourself. Let me start with a background slide that complements what Oscar has already stated. This slide comes from the IAE and shows the world energy supply to the year 2040. It indicates that the energy supply will increase and has to increase, but the portion of nuclear is not expected to increase very much. The nuclear portion is shown in yellow. Beyond 2040, the picture may change, demonstrating the long lead times for nuclear plants and technologies. Let me now turn to the fact that nuclear fission and fusion are both natural phenomena. In fission's case, it has occurred and is occurring inside the Earth. And in fusion's case, it is occurring, as we speak, in the sun and all of the stars. In this slide, I will show you the basic fission and fusion reactions. That is, the reactions that involve atomic nuclei, as opposed to chemical reactions, which typically involve the electrons that surround the nuclei. On the left-hand side is diagrammatically shown a neutron interacting with the uranium nucleus, which gets split. First of all, it gets transformed into U-236, and then it splits into barium and krypton, and there are various subsequent reactions. It produces several neutrons, which in turn then can impinge on U-235, thereby sustaining the reaction, and it produces energy. Fission involves large nuclei. Fusion, by comparison, typically involves small nuclei. And the diagram on the right-hand side shows the interaction between the nuclei of deuterium and tritium that combine temporarily, ejecting a neutron and forming helium, and also releasing energy. The really important thing to note is that as these changes in nuclei occur, there is a change in mass, and that mass is converted into energy. According to Einstein's equation, E is equal to mc squared, the release of energy is very, very substantial for a small amount of mass change. So if we represent just the fusion reactions here, the first reaction shows deuterium, denoted as 2H, fusing or reacting with tritium, denoted by 3H, and it forms helium and a neutron. And it releases 17.5 mega electron volts. Now, the neutron can be made to interact with lithium, but thereby forming more helium and producing tritium once again that can be used. So the overall reaction is, in effect, deuterium with lithium giving helium and releasing 22.3 mega electron volts of energy. Translating electron volts, which is an energy unit well known amongst physicists, but less so amongst engineers and even some chemists. So translating it into somewhat different numbers, but that are equivalent, we arrive at the conclusion that ideally 1 kilogram of deuterium requires 5 kilograms of heavy water and 3 kilograms of lithium, and it would yield 300,000 megawatt hours of energy, which would be equivalent to 135,000 barrels of petroleum. If you look at it in the other way around, again, this is our overall reaction, 1 million barrels of petroleum, which have an energy equivalent upon combustion of 2.2 terawatt hours of energy, that could be produced from 7.5 kilograms of deuterium combining with 22 kilograms of lithium. So you see the enormous difference in mass, because in one case, fission and fusion, it involves atomic nuclei as opposed to the electrons that surround the atomic nuclei. So let me say a few words about fission, and you probably have heard the announcement of General Electric and Hitachi GEH having been awarded by OPG the contract to build a small modular reactor at Darlington in Ontario. This would be a boiling water reactor slated to produce 300 megawatts of electricity. Site preparation is expected to start next year with the startup of the facility towards the end of the decade. It would result in significant CO2 emission avoidance. A few words about the appearance of this facility. On the left-hand side, I've shown two different pictures. They seem to show different plants. They're both from GEH sources, and I'm not sure which one will ultimately materialize. One of the things that we notice is the absence of the typical cooling towers that we are associating with nuclear plants. But if one actually looks inside the reactor system, we are looking at a single unit, about 27 meters in height and several meters in diameter, which is buried below the surface of the ground. It's located below the surface of the ground. One might wonder why that is so. The answer is not entirely clear, but the early considerations of all modern nuclear SMRs has revolved around the potential terrorist attacks. So if you put the plant below ground or the reactors below ground, that is safer from that perspective. This is a NuScale reactor, which is a reactor system that contains several modules combined into a plant. It's an integrated pressurized water reactor, with each one of the units producing of the order of 45 megawatt electricity. And this particular configuration is desirable if you want to have high steam quality, that is high steam, high pressure, high temperature steam at a high flow rate of the kind that you would want for SAGD applications in Alberta. This particular slide comes from a report that was done under the auspices of Alberta Innovates Technology Futures some years ago, and I'll give you the reference to it. So here we have a situation of several reactor modules being present in parallel in one unit. I've emphasized the SMRs because they are currently very much the focus of attention, and I'm going to raise some questions about them later on. Now, switching over to fusion, in contrast with fission. So what are the scientific and engineering challenges that, first of all, have to be addressed? Well, as we all know, the atomic nuclei are positively charged. And if you want to fuse them, you have to bring them together. Now, how to bring them together? There are different possibilities. But one way of doing it is to raise the temperature very, very significantly to 1,000,000+ degrees and to increase the pressure. Now, when you do that, then the atoms form a plasma. That is, the nuclei and the electrons are separate and moving freely. At very high pressures and very high temperatures, the nuclei, as well as the electrons, move very rapidly. And as you can imagine, when they move very rapidly and bounce and impact on each other, they may overcome their repulsive forces. And that's exactly what happens in the sun. Now, to maintain the fusion reactions either requires having a continuing burning plasma or creating a plasma repeatedly. And that's done in two basic approaches. So the one form of containing a plasma at elevated temperatures, 100 million degrees or thereabouts, and elevated pressures is by means of magnetic confinement. And this is the approach taken by many technologies, including the international development, which is called the ITER development in southern France. It's a plant that is under construction to demonstrate the science of nuclear fusion. It's not intended as a facility that produces electricity continuously, but as a key stepping stone towards a demonstration plant and then a commercial plant that utilizes the fusion phenomenon. A different approach from the magnetic confinement is called inertial confinement, where you start out with a pellet consisting of frozen deuterium and tritium, and you impinge a series of lasers, high-powered lasers, approximately 200, onto the surface of this small pellet, just a few millimeters in diameter. What happens as a result of the laser energy that is conveyed to the surface of this pellet heats up very rapidly. A significant portion evaporates, and as it evaporates, by Newton's laws or by the rocket effect, the compression occurs. And if the compression is sufficiently rapid, sufficiently high, and sufficiently geometrically smooth so that there is in fact concentric compression, you arrive at fusion, which produces heat, helium, and neutrons. So this insert of images shows the laser bay on the left-hand side, the chamber where the inertial compression takes place in the center, and on the right-hand side, it's difficult to see, is this tiny little pellet located in this big sphere, and the laser beams are impacting on that fuel pellet. Now, a lot of work is going on, and it's accelerating worldwide in the fusion area. At present, there's over 130 sites, with 2 sites in Canada where fusion work is being done. But the most active sites are in the United States, Europe, and in the Far East, China and Japan. Very interestingly, the private sector is stepping up with investments. You recall me mentioning the ITER facility. It's a $30 billion multinational initiative. But just over the last several months, several billion dollars of private sector investment have gone into the development of fusion development, principally in the United States and in Western Europe. We can deduce from that that there is a sense that fusion is closer than it used to be thought about, and that commercialization is probably not that far away, but we're still talking in terms of real major commercialization, decades, not years. In this slide, it's a busy table. I've tried to summarize and compare fission and fusion in accordance with a number of criteria. In the case of fission, the basic science is established, the basic technology is established, we know the raw materials. We know that fission reactors are complex. We now have the advent of smaller fission reactors, so-called modular reactors. There are some comments about safety, the inherent safety of fission reactors I would categorize as modest, but the actual performance is actually good to excellent, although there have been some near misses. A key issue is the radioactivity of the fission products, which tend to have very long half-lives, measured in centuries, in some cases millennia. Carbon emissions are low to none. In terms of their operation, carbon emissions do occur during construction and will occur during decommissioning. The capital costs of fission are high, which contributes to the overall high cost. And public opinion on fission is, to put it mildly, polarized. And that's never a good thing. In the case of fusion, you see what the corresponding responses to these criteria. The basic technology still needs to be proven. The complexity of fusion plants is exceedingly high at present, but I think that will really change. They do have the benefit of high inherent safety and actual safety, but the costs, both capital and operating, are still questionable, although in the case of the United States, the National Academy of Sciences and Engineering have taken a good stab at that and have specified at least the objectives. Just a few high-level comments to remind us all. Fission and fusion relevancy to Canada. These fission and fusion are large constant sources. Next click. It can be used, the electricity and the thermal energy output can be used for electrification, district and home and business heating. Next one, please. But then there are unconventional uses. One unconventional use would be extraction of bitumen from the oil sands. And that has received attention. And as I mentioned to you before, we've done work on that at Alberta Innovates, and I'll give you the references shortly. But then there's also the issue of conversion of oil and gas into different products, all of which are energy intensive processes. And we've already heard about hydrogen production, which is also energy intensive. And both fission and in the longer term fusion can make a significant contribution. I think it probably is self-evident that fission and fusion are new technologies, at least SMRs are new technologies, and with all the attendant benefits and challenges that they have for new businesses and new employment. So let me conclude by posing a series of questions. I will not answer these questions, but I really like to posit them with you. I don't think there is any real doubt that the complexity of current fission and fusion technologies should be reduced. The question is how to do this. There's kind of an intriguing question of whether whether a few SMRs are preferable to one larger fission reactor, and one can weigh that. What are realistic timeframes for fission? For fission SMRs, I think the end of the decade is quite realistic. For fusion, it is not the end of this decade. It's probably the end of the 2030s in terms of demonstration and 2050 in terms of actual application. There's this very interesting question, or set of questions, is fission, or are fission and fusion energy green, renewable, and sustainable? And one can look at that in different ways. How do we manage radioactive wastes? How do we inform the public better so that the public can make better decisions about fission and particularly about fusion? I think the benefits of fission for major industrial sectors are reasonably clear. The benefits of fusion are not yet clear, and it's really not yet clear what the long-term benefits are for the Alberta petroleum industry. But my thinking has led me to conclude that they are by and large strong benefits, in fact, essential benefits for the future of this industry. And then lastly, what action should Canada take? For fission, we have taken the decision to invest in SMRs. Canada has no real presence as far as fusion is concerned, although I'm very happy to say there are the beginnings. We now have the engagement with ITER, and I think that is very, very promising. And I'm also very pleased about the support that our American friends are providing us in the fusion area. Here are some references to reports that we've done on SMRs and SAGD and hydrogen production. There's a series of really good references on fusion by the National Academy of Sciences in the US and the IAEA. And the next one, you may all be familiar with references on SMRs in Canada, the call to action, and now the rollout of the action plan. With that, I conclude my presentation, and I thank you for the opportunity. And I acknowledge that some of this material comes from other sources, including Robert Fodotseev at the University of Alberta, and as always, Alan Offenberger's input. Thank you.
Very insightful, very decisive, substantial presentation describing the fundamentals of nuclear fission and fusion, the insights on the challenges and opportunities, and the configuration designs of these reactors, and how they can be deployed and when they will be deployed, as well as the programs that are in place to make them commercial, including the work at Darlington.